Today's video note 6.1, the mole. So we're going to decide what a mole is, learn about molar mass and conversion factors, and molarity. So please read Chapter 8, Sections 8.1 through 8.4 to get an idea of what your textbook authors have to say. So dimensional analysis. Notice what I have in the corner here. It's a dozen eggs. So dimensional analysis is using converting one unit into another, and it's called it's a technique. So you take the units you're starting with and you make them go away so that you're representing your numbers with a different unit. So a conversion factor is a true statement that's used as a ratio to cancel units. So 1 dozen equals 12 things, and that's what you see here, right? 12 things equals a dozen. 8 legs for 1 spider. 1,000 milliliters for 1 liter. So how do we do this? Well, in this one, we want to convert 4 years into minutes. So how many minutes are in 4 years? So we're not changing our value of years. All right, it's still 4 years, but we want to know in minutes what that is. So I know that 1 year equals 365 days, and I know that 1 day has 24 hours. So what I'm doing is I'm writing down things I know so that I can use them as conversion factors. Okay, so these are all true statements. So if I'm starting with years and I want to get rid of years, I put it on the bottom of a fraction that I'm going to multiply by. And I'm going to change those years into days. And then I'm going to get rid of those days by putting it in the opposite place and change it into hours. And then I'm going to get rid of those hours by multiplying by a factor that changes it into minutes. Now, notice the units are going to cancel out. So this unit is the top, like a numerator, all right? And then this is the bottom, a numerator over denominator cancels out. So I just have to make these true. So 1 year has 365 days, 1 day has 24 hours, 1 hour has 60 minutes. So years are going to go away, days are going to go away, hours are going to go away. I'm left with minutes. You may be wondering how many minutes that is. And it comes out to be 2,102,400 minutes. Okay? It's a lot of minutes. It's a big number, so I'm going to write it in scientific notation. 2.1024 times 10 to the 6 minutes. It's a lot of minutes. All right, does that make sense? Well, a year is going to have a lot of days in it, a lot of hours, a lot of minutes, so this is a lot of minutes. Okay. So metric conversions, the same way. I need to change 4.56 kilograms to grams. I know that there's 1,000 grams for every 1 kilogram. All right, that's I hope that you know, and I expect you to know the relationship between grams and kilograms. So I could take 4.56 kilograms, and I'm multiplying by a fraction. And that fraction is a conversion factor where kilograms goes on the bottom, grams goes on top. The reason I put kilograms on the bottom is so that they go away. Now I have to make this a true statement using my conversion factor. All right, so that means that 4,560 grams is the same as a kilogram. Okay. All right, 9,500 milliliters to liters. So liters is a unit of volume. I know that there's 1,000 milliliters in 1 liter. Okay, that's also something I hope that you know. So if you don't, memorize it now. So I'm starting with milliliters, and I'm multiplying by a fraction called a conversion factor where milliliters goes on the bottom so that cancels out. Change it to liters, make it true. 1,000 milliliters equals liters. Goodbye, milliliters. Hello, 9.5 liters. Okay, so you can also convert units on the bottom of a fraction and on the top of a fraction. Okay, so the top cancels with top, bottom cancels, top cancels with bottom, and bottom cancels with top. I can run 3.25 meters per second. Now, this slash really means that, okay? It's a fraction. So this is I'm going to multiply by a factor that's going to help me cancel out one of those units, okay? So I'm going to start with the meters. I want meters to go away. I want it to turn into kilometers. There's a direct relationship because I know that there's 1,000 meters in a kilometer, okay? And then after I do that, I want seconds to cancel out and turn into hours. Okay. So if I put seconds up here, it's going to go away because it cancels out. But I don't know the direct relationship between seconds and hours, so I'm going to change seconds into minutes. All right. Then I'm going to change minutes into hours. So there's 1,000 meters in a kilometer. That's true. Seconds are minutes. Let's see, a minute's bigger and there's 60 of them. An hour's bigger and there's 60 minutes in an hour. Okay, so what happens is second, even though it's over here, it's still on the top of a string of multiplication, so that goes away. Meters cancels out there. Minutes cancels out there. So when I'm done, my units are kilometers per hour. Okay, kilometers per hour is what I was looking for. So now I just do the math, and I find out that's 11.7 kilometers per hour. Okay, think I can run that fast? Is that fast? I don't know. Okay. So split units means top and bottom. You can also do multiplied units. So I can convert 12.1 centimeters squared to meters squared. So I know that there's 100 centimeters in a meter. But this is squared, and that's squared. So I need to take 12.1 centimeters squared. I need to get rid of it. But if I use this conversion factor, it's only centimeters to meters. So I have to do it twice so that my centimeters cancel out twice. And then I get meters times meters is meters squared. Okay? And I just use this conversion, 100, or equality, to fill in my conversion factor. And then it's 12.1 divided by 100 divided by 100, and I find out 0.00121 meters squared. And then scientifically notated, that's 1 times 10, 1.21 times 10 to the negative third meters squared. Okay. So conversion factors are used a lot in chemistry because, you know, like we say 12 for a dozen and a ream of paper, and then that's 500 pieces of paper, and a gross of bottle rockets is 144 bottle rockets. So sometimes in order to count stuff, we group it together and call it a whole thing. So a ream is 500 things. The gross is 144. A dozen is 12. So in chemistry, we use a thing called a mole. A mole, yes. A mole is huge. It's this number, 6.02 times 10 to the 23rd things. That's huge. That's a lot of things. Why do we use such a big number? Because those things that we're talking about in chemistry are atoms or molecules or formula units, and they're tiny. So a mole is important because it's going to let us count really small things by calling a whole bunch of them a mole, or half as many, half a mole. So this number, 6.02 times 10 to the 23rd, is called Avogadro's number. So if I say Avogadro's number, you should think 6.02 times 10 to the 23rd. If I say a mole, you should think 6.02 times 10 to the 23rd things. Okay? So a mole is a unit of measure, and for a little animal, its abbreviation, believe it or not, is MOL, because it's a lot easier to write MOL than MOLE. Okay? So a mole is MOL, it's a unit of measure, and we can count with it, we can weigh with it, and we can find volume in it. So how many are in a mole? How many molecules of water are in a mole? 6.02 times 10 to the 23rd. Molecules of H2O. All right? So in chemistry, we'll always be talking about something. Atoms of helium in a mole. 6.02 times 10 to the 23rd atoms of what? Helium equals 1 mole helium. All right, so all of these can be used as conversion factors. A mole of pencil, 6.02 times 10 to the 23rd pencils equals 1 mole of pencils. All right. Now, gases have an interesting feature. So here's a balloon filled with a gas. Here's another balloon filled with gas. Both of these balloons take up 22.4 liters of space. That's their volume. And both of them have a mole of particles. Okay. So only if they're at standard temperature and pressure. So here's a definition. At standard temperature and pressure, 1 mole of any gas equals 22.4 liters, takes up that much space. So the particles are so small that in that space, there's a whole mole of them, and we define them at the same temperature and pressure to keep it consistent. So the definition of standard temperature and pressure. Standard temperature and pressure is, these are the conditions, 1 atmosphere and 0 degrees Celsius. So if you have two gases at this pressure and this temperature, and they both take up 22.4 liters, then there's a mole of those gases. Okay, mass. How does mass relate to moles? Well, instead of counting atoms, we can weigh them. And so if we want to know how much a mole of anything weighs, we can go to the periodic table and find out. So the masses of 1 mole is called molar mass, or molecular weight, or molecular mass. All of those are the same thing. That's how much does 1 mole weigh. And 1 mole is Avogadro's number. Okay, so for carbon, if you have a mole of carbon, 1 mole, look, I use the abbreviation for mole, and the abbreviation for carbon is 12.01 grams of carbon. Notice it's 1 mole of carbon weighs 12.01 grams. Where did I get that? Yeah, from periodic table. 1 mole of CO2 equals, well, in a mole of CO2, you have 12.01 grams of carbon. You have 16 grams of oxygen times 2 oxygens in there. So you add that all together and you get 44.01 grams of carbon dioxide. So this is only if it's carbon dioxide. And how do I get that? Well, here's carbons and oxygens, molar mass. Okay, let's try this one. What? Look how many things are in aluminum sulfate. So 1 mole of aluminum sulfate. Notice I have to write the whole chemical formula because that's its identity. Whoa, we have 2 aluminums, 26.98 times 2, plus 3 sulfurs, 32.07 times 3, plus, what, 12 oxygen, 16 times 12. I know that looks a little messy, but all I do is add that all up, and I get 342.17 grams of aluminum sulfate for every mole of aluminum sulfate. Okay? So, 1 mole of any substance is equal to its mass from the periodic table. Okay, so here's what you have to remember. 1 mole equals the mass in grams from the periodic table for any substance's identity. 1 mole of a substance also equals 22.4 liters, only if it's of a gas at standard temperature and pressure. And 1 mole equals 6.02 times 10 to the 23rd representative particles. And then what are the representative particles we're talking about? We're either going to be talking about atoms, molecules, or formula units. Okay, atoms for elements, molecules for some elements and molecular compounds, and formula units for ionic compounds. So here it is again. That's what 1 mole equals. And so we can use dimensional analysis to describe how much we have of stuff. So if I have 12.5 grams of carbon dioxide, how many moles do I have? Well, I know that 12.5 grams of carbon dioxide, notice I have to put the unit and the identity, can change, moles can change directly into grams, or grams to moles if I put grams of CO2 on the bottom and moles on the top. Because of this, look, 1 mole equals a mass in grams from the periodic table. Since it's CO2, I have to add up 12.01, 16 times 2, and I get 44.01 grams for every 1 mole. This comes from the periodic table. So then all I do after that is I divide. 12.5 divided by 44.01 is 0.28 moles of carbon dioxide. Okay, let's try another one. We want to convert 19.9 moles of oxygen gas into grams. So the identity of oxygen gas is O2. So I have 19.9 moles. Look, I use my given. That's given to me. What am I trying to find? Find grams. O2. I'm going to change moles into grams. There's a direct relationship between moles and grams that I have to memorize. And then I always have a periodic table handy. So the number 1 always goes with moles when moles are with grams in a conversion factor. And where do I go get grams? From the PT. So it's 16 times 2. So we have 32.00. Notice I use 2 decimal places every time. Goodbye, moles of oxygen. Hello, grams of oxygen. Now I know that there's 39.8 grams of oxygen when you have 19.9 moles of oxygen. That doesn't sound right. 19.9 times 72. Let me check that. So guess what I'm doing? I'm getting out a calculator. So I said 19.9 times 32. And guess what? Harbin was wrong. That's not right. It is 636.8 grams of oxygen. That sounds better. Okay. All right. So, other mole conversions. If I had 3.59 moles of ammonia, that's I'm given that, I know that. How many molecules? Find molecules. There's a direct relationship between moles and molecules right there. So I can say 3.59 moles ammonia. Here I'm going to tell you NH3 is ammonia, but hopefully you get to know that one. So I know moles of ammonia can change into molecules of ammonia because the smallest piece of ammonia is a molecule. Now this is going to be different. The number 1 goes with moles every time, but when I'm talking molecules, I'm talking parts or pieces. So I don't want to know how much they weigh, I want to know how many there are. So I put in Avogadro's number, and I find out it's 2.16 times 10 to the 24th molecules of ammonia. Right. Let's try another one. Whew. How many moles is 63.8 liters? So this is what I'm given this. Find. So sometimes it helps to sort out your information. Given liters, find moles. Is there a direct relationship? Ooh, moles and liters right there because it says STP. So I'm going to take the 63.8 liters of what? Helium. Go ahead and make sure you put a unit and identity. I want liters on the bottom because I want those to go away. I want to find moles, so that's what I want to finish with. 1 mole is 22.4 liters of gas at STP. I can only use that if it's a gas at STP, and it tells me it is. So it's going to be 2.85 moles of helium. Okay, so using these 3 new definitions, right? The only one you have to calculate for is that one because every chemical has a different formula. Right? You can use these as conversion factors. Okay, so real world connections. Oh, look at those 2 cute dogs. Aren't they cute? Okay, so another use of moles is in solutions. But remember, a solution is a mixture. It has stuff dissolved in water. So the 2 parts are the solute, the smaller part, and the solvent is the biggest part. Okay, so miscible is just another way of saying 2 liquids. 2 liquids can mix. So you can have a solution of a liquid in a liquid, like water and vinegar. You can have a solution of a solid solute that dissolves in the solvent. Okay. So the way we describe how much stuff's in a solution is to talk about its concentration. Concentration is a description of what's in a solution. Okay. So the concentration of a solution describes how much solute is in the solution. So, all right, so here's, say we have our liquid, we'll use water as our solvent. And then we have particles dissolved. Okay, you can't see them, it all looks clear. All right, so we would say, maybe we'd say how much solute is in the solution. So it's 2 parts. Concentration has 2 parts, the solute and the whole solution. Okay, the most popular way chemists describe concentration is molarity. Molarity. Okay, so molarity is moles of solute. Please write this down. Please memorize it right now. Over liters of solution. Okay. That's the definition of molarity. The units are moles per liter, or you can write capital M. Capital M means moles per liter. You can write mole / L. Remember split unit, we talked about that earlier. Or you can just write capital M. But it means moles of solute divided by liters of solution. Okay, so what does 5 capital M HCl mean? It means 5 molar hydrochloric acid. Right, but what does that really mean? It means you have a solution, and that solution has 5 moles HCl for every 1 liter of H2O of HCl solution. Okay. 5 moles HCl per solution. Does that mean you have to have a liter? No, but if you do have a liter, you have 5 moles. So 5 moles for every 1 liter. You can use that as a ratio. What if I had half a liter? So 0.5 liters, then it would be 2.5 moles. So that when you divide it out, 2.5 divided by 5 equals 5 molar. Okay. So, molarity is a ratio that describes solute over solvent. Okay. So, we can solve problems with this using definition of molarity. What is the molarity of 2.5 liters of solution that was made with 45 grams NaCl? So let's write down our definition again. molarity equals moles solute over liter solution. Please, please memorize that. Memorize it. See what you can do with it. All right, we want to find this. Find capital M. Given liters. All right, we got 2.5 liters and 45 grams. All right, so what do we have to do with grams? Well, molarity is moles per liter, and it's moles of solute. So we have to take our 45 grams of NaCl and multiply it by a factor to change it to moles. All right, look, it's moles and grams. Moles are number one. Where do we go get grams from? The periodic table. And we go find that. We find out that 58.44 comes from, this is 22.99 from the periodic table. That's 35.45. So it's 58.44. Okay, so grams cancels grams, and I'm left with moles. And I find out that there's 0.77 moles of NaCl. Okay. Am I done? No, because I want molarity, which is moles of solute per liters of solution. So molarity equals moles of solute, 0.77 moles of NaCl for every liter of solution, but I have 2.5 liters of solution, so I have to divide it solution. Well, it is salt solution. Okay. And I find out I have 0.308 molar NaCl. So when you see this on a bottle, this capital M, it's telling you how much NaCl is dissolved in the solution. Okay, what else can we do with this? We want to know, find grams of calcium chloride given 25 milliliters and 3.5 molar solution. Okay, so here again, I want you to really work to realize that 3.5 M means 3.5 moles of calcium chloride for every 1 liter of solution. That's what this means. This is that. That is that. That equals that. Okay. So, and I want to find grams of CaCl2. Okay. And I'm given 25 milliliters. So it's saying, all right, I have this container. It's got 25 milliliters in it. And inside there is some calcium chloride. I want to figure out how many grams that got dissolved in it. So, milliliter, notice molarity is liters, but I'm given milliliters. So I have to start by saying 25 milliliters, and I'm going to convert it to what? To liters, so that it works with molarity. So I'm going to say milliliter to a liter. Okay. There's 1,000 milliliters in a liter. Please memorize. Memorize that. Okay. So now I'm at liters. I want to find grams. So the conversion factor only for this solution is there's 3.5 moles of calcium chloride for 1 liter of solution. So I could say 1 liter of solution has 3.5 moles of calcium chloride. How do I know that? Because that's what this means. That's what that means. Okay. And then moles of calcium chloride can change into grams of calcium chloride. How? From the periodic table, because 1 mole is the mass in grams of the substance. So, oh, excuse me, calcium, 40.08. Chlorine, that's an 8. Look at that 8. That's a crazy 8. Crazy 8. That's an 8. Okay. 35.45 times 2. So I find out that there are 110.98 grams of calcium chloride. So look what happens. Milliliters cancels milliliters. Conversions are super. This means 3.5 capital M. All I did was rewrite it, right? So liters cancels liters, and I can use it because this is the solution that I was talking about, right? Okay. And then moles of calcium chloride cancel, and I'm left with grams of calcium chloride. So I do 25 divided by 1,000 times 3.5 times 110.98, and I find out that in that solution, there are 9.71 grams of calcium chloride. So here's my little solution. I only have 25 milliliters of this calcium chloride dissolved. I know its concentration was 3.5 molar, so somebody dissolved 9.71 grams of calcium chloride into that 25 milliliters. Okay, to repeat, moles are groups of particles or anything that have Avogadro's number of representative particles. If you want to find molar mass, go to the periodic table in grams. Memorize what a mole means. 22.4 is just for gas at STP. And then we're going to use this technique, dimensional analysis, to solve problems. Set up a plan. Make sure each conversion factor is true. And then molarity is a way to describe a solution. Mixture of moles of solute and liters of solution, and we can calculate with it. Yay! Read your book, Chapter 8, Sections 8.1 through 8.4. All right, so there's hopefully what you learned and can do, but we'll keep practicing. Peace out.